Hey everyone, welcome back to the Foundry by Forge College. Let's get right into today's explainer, which is honestly a pretty pivotal moment in our applied Solidity development track. We are deep into the capstone project right now for building token sale mechanics. And in our previous lesson, composing sale components and refund strategies, you all did a truly fantastic job designing a beautifully crafted token sale contract. I mean, the logic looks pristine. But here's the thing, building it, that's really only half the battle. Now we have to transition from admiring a beautiful blueprint to actually stress testing it for the absolute chaos of a real mainnet deployment.
Picture this for a second. The hype is real, your marketing worked perfectly, and the countdown hits 0. Your code looks flawless on paper, all the modules from our previous lesson are just humming along in theory, but what actually happens when the network gas spikes and 10,000 wildly eager users hit your system at the exact same millisecond? Will your smart contract hold up, or is it going to crumble right under the pressure? That is the core engineering problem we need to solve today.
Okay, let's dive into this. Here is our engineering stress test agenda. First, we'll do a real-world reality check. Then identify system bottlenecks, add defensive coding patterns, run a load simulation, build a deployment checklist, and finally, conduct a final review.
All right, kicking things off with Section 1, the real-world reality check, going from blueprint to mainnet chaos. To actually survive that mainnet chaos, we really have to talk about the single biggest threat to your token sale, which is out of gas or OOG errors. Think of an unbounded loop in your smart contract like trying to cram an infinite number of clowns into a tiny mechanical clown car. You just keep stuffing them in one by one while trying to drive through a busy intersection. Eventually, the car simply runs out of gas, stalls, and fails right in the middle of traffic. It's kind of funny to picture, but trust me, it is an absolute nightmare for your users and your project's reputation when those transactions start failing left and right. Moving right along to Section 2, identifying system bottlenecks, basically figuring out exactly where the machine breaks. Now, what's really interesting about this engineering manifest is that it maps out a highly targeted stress test. We aren't just randomly crossing our fingers here. Notice how every single component, from the sales contract to the whitelist, the vesting, and the refund handler, has a specific tailored integration test. We have to ruthlessly verify latency within our gas budget under extreme pressure. Which naturally brings us to Section 3, adding defensive coding patterns. It's time to install our safety valves. You've got to see the difference here. That unbounded loop, that is our dangerous, endless clown car that severely risks an out-of-gas failure. But by contrasting this with bounded batch processing, which is just adding a super simple require statement to cap recipients at, say, 100, we instantly cap our gas usage. It makes the execution entirely predictable. This is absolutely crucial. It's the exact safety valve you need to keep the engine running smoothly, no matter what. And then we have your ultimate fallback, the circuit breaker pattern. Honestly, think of this exactly like the circuit breaker panel down in your basement. If an appliance suddenly starts sparking, you don't try to carefully rewire the entire house while the power is live, right? No way. You walk over and throw a giant, highly satisfying physical switch to instantly cut the electricity. By putting a simple on-chain pause and unpause state modifier into your contract, you're giving yourself that exact same emergency logic gate. You can immediately stop the system if some critical, unforeseen bug surfaces post-deployment. Section 4 already. Running the load simulation. This is where we test the engine locally. You must, absolutely must, test these new safety valves in an isolated, perfectly safe environment. These 4 imperative steps outline exactly how to spin up a local Hardhat profile and run a load check script programmatically. By doing this on a local node, we aren't risking any real funds, we certainly aren't paying ridiculous mainnet gas fees, and we aren't exposing our private keys to the open internet. It is literally the perfect sandbox to just sit back and watch your system perform under duress. So the crucial point here is this specific number, 50. During this local simulation, we want to run exactly 50 sequential, deterministic simulated buys. Actually, scratch that. It doesn't just have to be 50, but 50 is the magic number here. Not just 1 or 2, and definitely not 10,000. 50 gives us a highly accurate baseline metric for our average gas usage and transaction latency, and it doesn't take hours to compute. It's basically the optimal sweet spot for capturing reliable, actionable metrics. Next up, Section 5, building the deployment checklist. Time to compile the final sign-off. Before we actually look at the checklist itself, I really want to highlight this concept. Throughout all the advanced learning programs and courses we run here at Forge College, we heavily emphasize this principle of graceful degradation.
Basically, it simply means you should keep your main payment function alive and working flawlessly, even if a secondary external system completely fails. So if an external oracle goes down, your users should still be able to interact with the core token sale contract. Never, ever let a secondary system crash your primary mission. All right, let's walk through the critical checkpoints. Honestly, treat this as your ultimate pre-flight sign-off sheet for system reliability and observability. First, you verify your local integration snapshot based on that 50 by test we just talked about. Next, set your strict gas budget estimation thresholds. Then, define the gating criteria that's going to allow for future upgrades. And finally, initialize your post-deploy observability hooks so you aren't just flying blind once the contract is live. Check all these off, and you've built a structurally sound foundation. And finally, Section 6, Final Review and Next Steps. We're prepping for inspection. Okay, so you've done the heavy lifting. You've gathered the data, and your checkpoint is fully verified. To summarize, these concrete metrics, I'm talking about your deployment snapshots, your latency records, your test outputs, and your completed checklists, these are the exact inputs your reviewers are going to use. They're going to dig into these numbers to surface any weird edge cases or bizarre system faults you might have missed during your own testing. Which brings us to one last, slightly terrifying but provocative question. Will your smart contract actually survive the mainnet stress test? Well, because you've mapped your bottlenecks, you've installed your circuit breakers, bounded your batch processing, and rigorously verified your checklists, the answer should be a resounding yes. I highly encourage you to head over to forge.college to learn a ton more about comprehensive Web3 deployment mechanics, scalability constraints, and all the other advanced topics we've got waiting for you. Thank you so much for joining me on this explainer today, and as always, keep building for the real world.